Our project is AI for behavioral discovery. I'm Shreyas.
Elias?
And I'm Ben. So, in the last 30 years, technology has advanced tremendously, namely technologies like smartphones and the internet. And along with this has been a significant increase in the amount of electromagnetic frequency radiation in our environment. At the moment, these long-term impacts on life are not well understood. Our project seeks to answer the question, can machine learning learn the behavioral effects of EMF radiation on biological systems?
So we want to use a process. We want to use machine learning, and the way machine learning works is that models are trained to identify patterns that the human eye cannot easily recognize, and this is highly scalable since we can use a lot of data. But two of the issues we're facing with machine learning is shortcut learning, where models are learning the easiest feature instead of the features that we want to learn. Like for example, in the past, we noticed that the model is learning what time the bees are most active rather than if the electromagnetic field was on or off. And another issue is with noise, which is kind of like the background of the image. So the models are just learning from the background rather than from the actual things we wanted to focus on.
So our approach was to use simulation data first to get a better understanding of our model's behaviors and to reduce shortcut learning. So over here is kind of a short snippet of how our simulation data looked like. We also used camera recording data to record ants and bees. Ants over here, and we have bees over here. And to analyze our videos, we were going to use a neural network, a deep neural network, specifically a convolutional neural network, which is a type of image classification model, which is particularly good for our problem. And the goal was to understand the role of electromagnetic stimuli and its impact on multiple species.
So our experimental setup was intended to try to reduce as much noise as possible. Noise being like light, stuff like factors we couldn't control, but variables that didn't have any impact, that shouldn't have any effect on the experiment. So we used Helmholtz coils to provide a uniform magnetic field over the test subject, which is the petri dish in the middle. We also sealed off light cavities to reduce noise, which is light pollution. Like lights would turn on and off outside, but inside we could try to control it. And we use a Raspberry Pi and overhead camera to record data. So we also revamped the software pipeline. We used Slurm to access GPUs, but earlier attempts at pipeline was very unreliable. As you can see, here's our new pipeline, which is a bit faster, and even though it did take it still takes pretty long, but it's much faster than in the past.
So for our model architecture, we used CNN, particularly AlexNet, and this is kind of the way it works. So we take a input video of the bees moving, and we run it through convolutional and pooling layers repeatedly to eventually get like the final output, which just says if the field is on or off. And we added a channel dimension so we could read multiple frames at a time.
So to visualize what our model is looking at, we use GradCam. So GradCam is a tool that highlights the weights of a model. As you can see here, there's a bee in that upper left-hand corner, and the model is looking at that in a way. It's very similar to a heat map. The more red, the more the model is looking at that specific spot.
So as I mentioned earlier, the point of the simulation data was to get a better understanding of our model and to reduce the shortcut learning. So with all models, as Shreyas mentioned, models try to learn the easiest possible thing. So our main concern was that we weren't learning motion. So over here is a final iteration of our simulation data. And you can see we have a fixed center home, which is the green square. We also have the bee, which is the blue ellipse-looking object. And it has and essentially we have two possible states. So either the field is off or it is on. Over here is kind of an example of how it looks like when the field is off. The path is linear, whereas when the field is on, the field becomes curved. And some things we also kept in mind were to have a constant and normalized speed across all trajectories. So that would reduce the possibility of our model learning based off of speed rather than motion. We also have a lot of varying features. And the point of the varying features, like varying the field direction, varying the field speeds between trajectories, was to essentially give us a better distribution. So red over here is the field on, blue is the field off. And you can see our distribution is pretty good. So that reduces the likelihood of our model learning based off of location. And we also had 7 continuous frames per sample, which the point of doing so was to further encourage our model by learning motion rather than just location. So our results were that we got about 90% accuracy. As you can see over here, it converges. So that's pretty good. And to make sure that we weren't learning based off of location once again, we ran our data through a naive Bayes classifier, which is a famous classifier that's particularly good for one-dimensional data, like giving it a coordinates list rather than images. And you can see by this confusion matrix, it got about 55% and it collapsed. And that means that our location, it was really, our coordinates were really well distributed. And then also if you take a look at this decision tree with blue being filled on, blue being filled off, red being filled on, you can see our decision boundary was really complex. So once again, that reassured us.
So after the simulation data, we started real data with ants. So we purchased a commercial acrylic case and filled it with ants and this like blue food gel. And we recorded the camera data and trained on uncropped data, no background data, and a control set as well.
So our results for the ant data was about 90%. And for us, that was suspiciously high. So the reason why we were suspicious is for a few reasons. For one, we recognized there was a few issues with our setup. Over here is a video, but you might not even tell it's a video because the ants weren't moving much. They weren't really familiar with the environment. Also, we'd be recording on hours on end, which would mean that they could die over the hours of recording. Meaning there was no behavior to analyze, yet the model correlated something. Also, we recognized there could have been lighting issues. So over here, although it looks really steady, it might have not been as steady as we thought it was. And also, if you take a look at this grad cam plot, you can notice that the model isn't even focusing on the ants. Blue, once again, is where the model is not focusing on, but that's where the ants are. And the red is where it focuses, and that's where the background is.
So we addressed the issues both by back. So we trained on ants and bees. So we tried to address issues relating to bees through background subtraction, which is like differences between the past frames. We also did cropping. So we cropped out the ants as a control, and we also cropped out the background to see. And as you can see in GradCam footage, if you look at the ants the ant GradCam before we plot, the CNN is looking at the background, but after we crop, the CNN is looking at the ants, which is a market improvement. That's just an image of the noise in the ant data, which is really weird. Okay, so our conclusions is that we have like pretty promising results, like the accuracy for ants and stuff, but our project's mainly based on behavior, and unlike other earlier research, which is often the cellular level, so we have to focus on covariates and stuff that can impact our training. So a big thing is just keeping data clean and making sure we can focus on behaviors that we can control. And yeah.
For future work, our main goal is to perfect the experimental setup, and we could do that by reducing noise and try to make it into the most perfect possible conditions. And we're also going to try to explore like different models, especially those with temporal capabilities.
Like example of that is this vision transformer, which uses the transformer architecture to analyze images.
So we just like to conclude the presentation by saying thank you to our advisors, Professor Richard Martin and Professor Richard Howard. We'd also like to thank Yvonne and Jenny, and we'd like to thank everyone at WINLAB for making this such an amazing experience. Any questions? Yeah. Hey, what'd you say? For the simulation data? The real data. So essentially, our model. So the question was, how did we get 90%? So in our model, when we trained, we had either the field was on or it was off. And when we recorded the videos, we converted all the videos to grayscale, and then we give the model our label data. So in those, so when it trains, it has which class corresponds to which videos and which frames. and then when it tests, it doesn't know. So and we were fortunate enough to get 90%, but it's not really accurate though.
So we use like k-fold cross validation, which allows us to train on more data along getting more accuracy, and that and we also predicted 3 classes, so 90% accuracy is pretty high. We compared that like a coin flip.
I'd
Three
also like.
faces is
Oh yeah, if you want.
with 3 faces is around 33%.
Also, we did experiment with some of our trials with other experiments, like trying an 80-20 split. So that would let us train on more of the data, so like 80% of the data, and only test on 20. So ideally, we could get a better model that was like better trained for testing. Any other questions?